Hi everyone, my name is Eric. I currently work as an electrical instrumentation and controls engineer based in Chicago, and I have a bachelor's in electrical engineering. Today's topics will be in digital systems. More specifically, we'll be getting into Kavanaugh Maps, how you would find the minimized sum of products for these kinds of problems. And yeah, so I'm going to go through a couple problems today, and we'll work through them together and try to find the best solution for each of them. So let's get started. So very quickly, what a Kavanaugh map is basically kind of like a tablet, and essentially what you would be given is a bunch of ones and zeros, kind of telling you what the logic Boolean expression should be, or the most minimized, in this case, minimized sum of products that you can express. And so for most people, when you think of Booleans, you think of and or gates, right? So when you have your and gates and or gates, but in this case, what we're doing is we're trying to figure out, just based on looking at a Kavanaugh map, what the simplest logic expression should be. So if we were given this, where we have AB on the left and then a C at the top, right? And in this case, we can see that there's ones in spots where there are, and then there's empty spaces in the other. So our priorities should be only focused on the ones that hold a one value in it, saying that this is expressed and this exists in this logic expression. And so in this case, one of my first kind of recommendations is that whenever you see a single numeric value and there's no associated numbers around it, first identify what that one is, right? So we can see that we have 0, 0, and then we have a 1. For 0, 0, we have 0, 0 for AB, and then for C, we have 1. And so what that means is that AB is prime prime, and then C is just 1. So in this case, we can already express what this individual one is. So it would be AB prime, and then because C is also represented, but it's not primed, it's just a simple non-prime. And then the only thing we have left is to add these two. And so what's different about these two is that you don't want to express these individually, although you can. It'll just make things a little bit trickier for you because you're going to have to minimize the sum of products, meaning that you have to express it in its simplest form. My recommendation is actually taking the combination of both of these together. And so the way you can do this is that identifying which ones coincide and which ones coexist together and which ones don't. And so what we see here is that um, because it's in this column, the C column of prime, we do know for a fact that C prime will exist. So we do know that C prime will exist because there has to be a C prime for 0. Now what's different here and trickier is that we see that the A, which is the first numeric value, is non-prime. So we actually know that as well. So we know that it's non-prime, and the B is 0, 1. And whenever we see a 0, 1, the way that's actually represented is that we don't represent it at all. So in this case, it'd be A, because A is non-prime, B does not exist, and then C would be prime. So the way you would express this is just A, C prime. And so your simplest function would just be A prime, B prime, C plus A, C prime. And that's what you get as the solution for the some of the products for this Kavanaugh map specifically. So awesome. I'm going to erase the board and we're going to go through a little bit of a trickier one and kind of work through them one by one and kind of going through how what's the easiest way to approach each of them. So awesome. Okay, awesome. So I have two Kavanaugh maps here. We're going to start with this one on the left-hand side first. So this one looks kind of trickier because now we see a bunch of ones. So it looks like, oh my God, there's gonna be a bunch of logic expressions we're gonna have to put together and add and subtract or figure out or minimize the sum of the products and make it easier for ourselves. But actually, it's very simple. And the reason why I say this is because the first thing we know is that we have the AB on the left side here and the C represented at the top. So the C represents the columns, the AB represents the rows. And just by looking at this, if you remember, whenever we have a 0, 1 represented and we have both those slots filled out, then we can essentially say that the C in this case is canceled out. And so in this case, the C doesn't exist for this expression because it's filled in for both the rows for here and both the columns. And so we already know that C cannot be prime, it cannot be C non-prime. So we know that that's not going to be part of the solution. However, the AB is the part we should still look at. And if you remember, I said to kind of identify if whenever you see ones kind of next to each other, you should put the sum of them together, and it'll make your life easier. But in this case, if you have four that are kind of together like this in a square, you actually connect all four, and it actually makes your life a lot easier. And so, like I mentioned, the C is not something we should consider. It's not going to be important for this expression to find the minimized size sum of the products. So in this case, all we do is we look over here. We see that the A is represented as 1. So the A for sure exists. But does the B exist? When you look at it, we have B as non-prime and then B as prime. So what actually happens is B prime and B non-prime does not exist either. So actually the solution for this problem is just A. So that's the minimized sum of the products for this problem. And like I mentioned, you could go one by one and find the expression that way and kind of breaking it down. But if you take it from this side where you see all the ones all together bunched up together, you might as well just put it together and then configure it out that way. And like I said, the way you do this is that the A is represented in this column, the B is represented here. So the A's are 1, 1, which is non-prime. And so that's why we know for a fact it has to be A. If we had it here, so if we had it here, 1, 1 like this, and 1, 1 here, it would actually be the opposite. It would actually be A prime, and then the B's would cancel out anyways, right? Because 0, 1. So then in this case, the solution, if the problem was up here, would be A prime. But in this case, because we had it down here, it's going to be this. Okay? Make sense? Awesome. And now the only one we have left is this Kavanaugh map. This one, now we're bringing in a fourth variable because we previously just had C, but now we have CD. And so what we do here is that we kind of look at what we had previously and we kind of see kind of anything that sticks out to us right away. And in this case, we have two rows that are filled out completely and all the columns do exist, but they're kind of like, in this case, we have the column or the row up here filled out and the row down here filled out, right? And so what I recommend, and it's kind of what we saw over there, is that in this case, the C's, because it's represented over here, and the D's, and there's a 1 for each of them, we don't have to actually worry about CD at all because it cancels each other out. So CD cancels out each other out over here and over here. And so we only have to look at this row and this row. And like I mentioned previously is that when we look here in the first column, this represents the A, this represents the B. So the A is 0, 1, and what, like I mentioned previously, 0, 1 means A prime A, so that becomes 0, or we don't consider it, it's not in the expression. So the only thing we have left is 0, 0, which in this case is just B prime. And so that's our solution for this Kavanaugh map. Awesome. That's how you basically solve for these kinds of problems. If you guys have any questions, leave it in the comments below. But that's all I have for today for digital systems and Kavanaugh maps. So thank you. Appreciate it.